Hey everyone, so welcome to the video where we actually start to evaluate a few different types of limits. And one of the first methods that we'll encounter is how to evaluate limits through factoring. And before we actually evaluate the limit, just remember that if you have some functions, let's say I have a limit as x approaches 5 of 2x squared minus 10x. So if this is the case, I'll just write plus 4. Doesn't matter, but you'll get the idea. So if this is the case and I realize that, okay, there's no random holes in the function, there's no asymptotes that I need to worry about, and basically it's just a nice, smooth, continuous function. But instead of doing a table where I approach limit as x approaches 5 from the left-hand side and approach the same limit from the right-hand side and seeing which value they converge to, one of the things is that if this is a nice, simple, continuous rational function, then I can just plug in the number 5 in here and I'll get the answer. So this answer right here is 2 times 5 squared, so that's 25, minus 10 times 5, so that'll be 50, and then plus 4. Okay, so I'll have 50 minus 50, so that's 0, plus 4, so that'll be 4. So my answer is 4. But let's say I have some other functions. Let's say now I have a limit as x approaches 5, but this time I have x squared minus 25 on the top and x minus 5 on the bottom. So with our quotient laws, where basically we learned in a few videos back that in the properties of the limits video, that this is the same thing as saying limit as x approaches 5 of the numerator, so that's x squared minus 25, and limit as x approaches 5 of the denominator, which is just x minus 5. Both of these functions individually are really nice functions, right? X squared minus 25 doesn't have any random holes asymptotes, so I can just plug in 5, and I'll get 25 minus 25, so that'll be 0. On the bottom, I'll get 5 minus 5, so that's 0. But total, in totality, right, I can't evaluate this because 0, 0 is undefined, it does not exist. So is the limit truly does not exist? Well, before we jump to that conclusion, what we need to do is see if there's a way we can factor out something from the top, factor out something from the bottom, basically get the numerator and the top into its most reducible terms, and then see if we can cancel something out. So what I mean by that is, if I evaluate the numerator over here, this is the same thing as saying x minus 5 times x plus 5. I just factor the numerator. The denominator is just x minus 5. It's to the degree 1, so I can't really uh, further factor this out. So when I get this, I see that, okay, there's a common term of x minus 5 on the top and the bottom. Basically, I cancel these terms out, and I'll be left with x plus 5. So this right here is the same thing as saying limit as x approaches 5 of x plus 5. Okay, now I can plug in 5 in here and I'll get my answer is 10. So my answer does not exist. Okay, it's actually 10. When you graph this function, okay, when you graph this function, and by this function I mean x squared minus 25 over x minus 5. Okay, it will be a line. It'll equal this function x plus 5. So it'll start at 5 over here, and it'll keep on going. This will be negative 5. Right, it'll be a straight line, but um, uh, at the point 5 right here, somewhere around here, there'll be a hole. Okay, and then it'll keep on going again. So basically, this function, x squared minus 25 over x minus 5, is almost equal to the function x plus 5 because I just reduced the numerator and the denominator, cancel out the common terms. Um, but the only caveat is that at the point x equals 5, this function isn't defined. Okay? But at the point x equals 5, this function is defined. So basically, these functions are equivalent to each other at infinitely many points, except for one point, which is x equals 5. Okay? And most of the times when you're going to evaluate limits, you're going to have a denominator equaling 0, so you're going to have to see if you can factor it out. So let me do another example. So let's say I have a limit as x approaches 4, and I'll have x squared uh, yeah, it was similar to this. Okay, let me just do x squared minus 16 over x minus 4. So if this is the case, what happens? I can't plug in 4, because if I do that, I'll get 0 on the top and 0 on the bottom. Let me see if I can factor it out. If I factor it out, this function on the top becomes x plus 4, and then x minus 4, right? And now what I can do is cancel out the common terms of x minus 4 from the numerator and the denominator, and I'll be left with x plus 4. When I do that, limit as x approaches 4 of x plus 4, that's a nice simple function. I can evaluate that. I can just plug in x for 4 and I'll get 8. So that's my answer. For the next slide, let me do a couple more examples so you get the hang of factoring limits through, or evaluating limits through factorization, and we'll be done with this then. So let's say I have another limit. Let's say that x approaches uh, 3, okay, and I'll have x squared minus 5x plus 6 on the top, and then I'll have x minus 3 on the bottom. So let me see what happens if I plug it in. Just try plugging in, try substituting every single time, okay? If I plug in 3 on the top, I get 9 minus 15 plus 6, so that'll be 0. And then x minus 3 on the bottom, that'll also give me 0. So let me see if I can factor out the top. The top, I can reduce it, right? I mean, this is a simple quadratic equation. I can factor it into x minus 3 and x minus 2. Okay, the sum is negative 5, the product is 6. So this is the factorized form. And then this is x minus 3 again. And then this stays the limit as x approaches 3. So the common term is x minus 3 on the top and the bottom. I cancel them out. And then I can plug in 3 over here, and then I'll get 3 minus 2. So my answer is 1. So let me do one last example, and that'll be it for this. Okay, and this one is a pretty simple example, so let me just write it as limit as x approaches. I'm making this up as I go, so I actually don't know where it approaches, but let's just say it as on the denominator I'll have x minus 4 squared, and on the top I'll have x squared minus minus 8x plus 16, and then I'm gonna multiply that by 2x plus 6. Okay, so I kind of just made it up on the go, but let's see what happens. So if I have this function over here, what do you think will happen? On the top, I have if I plug in 4 first, I'll get 16 minus 32 plus 16, so that'll be 0. And 0 times anything is just 0. And on the bottom, I'll get x minus 4 squared. If I plug in 4, I get 0 squared, which is 0. So this limit does not exist. Well, let me see if I can factor out the top first, okay? So if I factor it out, let me just do it in a different color. This right here will change into x minus 4 squared. Okay, it's basically x minus 4 times x minus 4, factor the 4 out, and then 2x plus 6. And in the denominator, I'll have x minus 4 squared, which is just x minus 4 times x minus 4. Yeah, so I have two x minus 4 terms on the top and two x minus 4 terms on the bottom. Each one of them cancels out with one another, and I'm only left with 2x plus 6. So my new limit, or equivalent limit, is now limit as x approaches 4 of 2x plus 6. And now this is a nice function. Doesn't have any holes, doesn't have any asymptotes. I can just plug in 4. And I get 2 times 4, which is 8. 8 plus 6 is 14. So my final answer is 14. So that's it for this video. I hope you got the idea of how to just plug in the numbers and see if you get 0 or 0 or something like that. Um, see if you can factor out something on the top and the bottom. And that's pretty much it for this video. Hope you liked it. Hope you learned a lot. In the next video, we'll go over a couple of different methods of evaluating limits. So I'll see you then.